Hello, good morning, everyone. I am the next speaker in this series of introductory summer school and refresher course in astronomy and astrophysics this year. I will be conducting a couple of lectures on compact stars, which is also my field of research. Um, so, um, if you you can interrupt me in the middle of my talk also if you have urgent questions, or otherwise of course you can wait until the end of the talk, and I will be happy to answer your questions. So let's get started. So what do we mean by compact stars? So you have already had a few lectures on basics of astronomy and astrophysics in this school. So what we are referring to as just a second. What we are referring to as compact stars is this class of objects you see at the end point of evolution of stars. So the normal stars that we see, like the sun, they are comparatively light stars. So there are stars which are much more massive than the sun. So I'm sure you had some lectures on evolutionary sequences and Hertzsprung-Russell diagram, where you have seen different evolutionary sequences of stars depending on their mass. And likewise, we are talking about the lives of stars here. So as you can see, the top line here. So this corresponds to low and medium mass stars like the sun. And these end in compact remnant objects called white dwarfs. And high mass stars, these end, so this is typically between 8 and 25 solar masses. These kind of stars end their lives in supernova explosions. I'm going to talk about what these are. And they can end as either neutron stars or black holes. So these are the objects we are calling compact stars. And why is it so? Because white dwarfs typically have masses which are even smaller than that of the sun, but with a radius of around that of the Earth, so nearly that of the Earth. So their densities are around 10 to the 9 kgs per meter cubed. On the other hand, neutron stars, they have masses around 1 to 2 times that of the sun within a very small radius of 10 kilometers. So if you do this back of the envelope calculation of calculating the density given the mass and radius, you will see that the density of neutron stars is as large as 10 to the 17 kg per meter cube. So this is already comparable to what you have inside a nucleus. A nucleus is the dense part of an atom. So this is comparable to the nuclear density. So actually neutron stars are the densest forms of matter in the universe. So this is why we are studying compact stars, because they represent exotic physics. And we want to find out more by observing these objects. So let me briefly tell you about how these objects are formed in the first place. So you must have had some lectures about the stellar life cycle, about at the bottom you see the life cycle of the sun. And so as you know that ordinary stars like the sun, they generate thermal energy by nuclear fusion of light elements like hydrogen. So the stellar structure is determined by a balance of thermal pressure support due to nuclear burning and gravity, which tries to collapse the star. So Dipankar must have talked about the stellar structure. And so what happens in ordinary stars like the sun is that this hydrogen fuel burns to provide this thermal support. And then when the fuel is exhausted, the thermal pressure support decreases. So the core now begins to contract under gravity. This raises the temperature and initiates helium burning, which is the product of hydrogen burning. And then helium burning produces carbon. Now, in low mass stars like the sun, nuclear burning does not proceed beyond carbon because of the mass of the star. The mass of the star is low, so the temperatures attained in the center are never high enough to initiate carbon burning. So what happens is that the sun, you see at the bottom panel, the life cycle of the sun. So these end as carbon-oxygen white dwarfs. So I'll come I'll come to the structure of white dwarfs later in this talk. So, in more massive stars that we were talking about, so say 8 times or up to 25 times that of the sun, what happens is that these stars now reach sufficient temperature in their core and also sufficient pressure to cause carbon to burn. And in this way, carbon produces oxygen, and then this nuclear burning continues, producing heavier and heavier elements like oxygen, neon, magnesium, silicon, and iron. And these form an onion-like structure like you see on the left-hand side. Okay. Now, what happens when iron is produced? We know from nuclear experiments that iron or iron group of elements have the maximum binding energy per nucleon. So fusion of iron does not produce more energy and nuclear burning stops at this stage. So when fusion ceases, what happens? As you know, in the stellar structure, you have seen that thermal pressure support provides the stability to the star. So now that the thermal pressure support is gone, the core starts to collapse. Now, this is what leads to a supernova explosion, but the picture is way more complicated. And actually, what even I'm talking about in this talk is a very initial, a preliminary discussion, because supernova is an active topic of research. There are a lot of like 3D simulations which are still trying to understand a lot of properties like neutrino transport, etc. So this is the basic idea of what goes on inside. अभी हम लैपटॉप चले. As the outer layers collapse towards the center, the rapidly shrinking core, this starts to heat up, causing photodisintegration of the iron nuclei, and this produces helium nuclei and neutrons, as you can see from this cartoon on the top and also these equations on the right. So these helium nuclei further split into protons and neutrons through photodisintegration. Now, as the core density increases, it becomes favorable for these electrons, from the electrons and the protons, to combine through a mechanism called electron capture. It's also called inverse beta decay, which produces neutrons and neutrinos. So now what happens is that okay, so let's go further. And so neutrinos, now these neutrinos which are produced, neutrinos are particles which rarely interact with normal matter. So what happens is neutrinos escape the core and take away energy from the system. This accelerates the collapse. Now the collapse may be stopped. Now the question is, what will be the end product of this? Is it going to collapse into a black hole? Well, there is a possibility of halting this collapse through degeneracy pressure. So I will come to what is that, and also through strong nuclear forces. So if, because you saw that neutrons are produced in the center, in the core, and if the neutrons, they are dense enough so that these infalling layers can be halted by the strong repulsive nuclear forces, and this can result in a rebound and a shock wave to be produced. So once the collapse halts, this infalling matter rebounds, producing a shock wave which is propagating outward. So the shock wave now starts to dissociate the heavy elements which are there in the outer layers of the star. And because of this, energy is lost and it can stall the explosion. But then neutrinos, which are being emitted from the core, these carry a lot of thermal energy. So it is thought that these neutrinos, they transport energy, they revive the shock, and therefore they cause the supernova to explode. So you see this beautiful picture on the right. If you go on a site like NASA, you will see that there are lots of beautiful pictures of supernova explosions that have been observed. So this is the rough mechanism of the core collapse supernova. Now, we were talking about degeneracy pressure, right? So this is one mechanism which is thought that can halt a core collapse explosion. Now, what is this degeneracy pressure? Now, to understand this, we have to think of these subatomic particles. Now, these electrons and neutrinos which are present inside these atoms, these have half integral spin. And they are called fermions. They obey a different kind of statistics, Fermi-Dirac statistics. This is, if you have taken a course on statistical mechanics, you would know about this. And these are contrary to those of photons. So for example, photons, they have integral spin, and these are bosons. They obey a different kind of statistics called Bose-Einstein statistics. So electrons, neutrons, these class of families, fermions, they behave differently from photons. And so what is this different behavior? So as you can see on this top cartoon, so electrons and neutrons, which are fermions, so you see on the left, these are bosons. So bosons, when the temperature is very low, bosons can all go to the lowest energy state. On the other hand, fermions, they obey something called the Pauli exclusion principle, which means that they are forbidden from occupying the same energy state. So this means it's almost like the social distancing that we see today. So they are not allowed to crowd to the same energy level, which means they are forced to occupy higher energy levels. And therefore, this results in higher Fermi energies, higher chemical potentials, and therefore also higher pressure in the system. And this pressure is called degeneracy pressure. So now, because of this pressure, this repulsion among these fermions, this can also result in halting the core collapse or providing a pressure support to the system. So as we talked before about hydrostatic equilibrium, remember that we said that gas pressure. So earlier in the case of normal stars, this was thermal pressure support. So now this is coming from a quantum mechanical pressure support. So if electrons, that we were talking about electrons, so when in the beginning, when electrons provide this degeneracy pressure support, they result in a remnant which is called the white dwarf. But then this depends on the progenitor mass. If the mass of the normal star, which is collapsing, is so this results in a white dwarf, which is okay, I will come to this. So 1.4 solar mass, 1.4 times that of the sun. So this results in a white dwarf. But if the original progenitor mass is much larger than this, then it cannot be supported even by the electron degeneracy pressure, if it's too massive. So in that case, again, it starts to collapse further. And then neutrons, which are heavier than those of electrons, these provide the degeneracy support. And in that case, the core is comprised mainly of neutrons, and it's called a neutron star. So, but then if the mass of the progenitor star is so large, so high, that it cannot even be supported by neutron degeneracy pressure, then it ends in a black hole. So we'll come to more discussions about this. So this concept of white dwarfs and degeneracy pressure was first proposed by Chandrasekhar. So he said so it was shown that electron degeneracy pressure supports white dwarfs against gravitational collapse. And this mass, so the maximum possible mass for a non-magnetized white dwarf was shown by Chandrasekhar back in 1931 to be around 1.44 solar masses. So this comes from the calculations of the fermions. So I will come to this in the next lecture. This can be calculated. And so, like I said, if the masses are in excess of 1.44 solar mass, then the electrons become relativistic and the degeneracy pressure is not sufficient to support the gravitational collapse of the star. Now, as you probably already know, so this concept was challenged by Arthur Eddington, who was the supervisor of Chandrasekhar. But then when observations supported observations came a bit much later. But when it was confirmed that indeed this is the case, so Chandrasekhar was awarded the Nobel Prize in Physics in 1983. So here on the right hand side, you can see the calculation, the relation between white dwarf masses on the x-axis and that of the radius on the y-axis. And like we said that the maximum supported white dwarf mass is around 1.44 that of the sun. So we'll come to this detailed calculation in the next lecture. Now, so this is a summary slide, a summary picture of what goes on in the core collapse supernova that we talked about until now. So like we said, when the core exceeds the Chandrasekhar limit, which is supported by electron degeneracy pressure, then the core starts to collapse. Protons combine with electrons to form neutrons, and this core shrinks. The neutrons, like I said, neutrons have nuclear densities, so these bounce back in falling matter. The shock wave starts to slow down because of dissociation by dissociating heavier elements in the outer layers, and then the shock wave is accelerated again, so it is revived by neutrino flow. So this is the mechanism of the core collapse supernova. It's also called supernova type 2 because there are also other types of supernova. So this is, can you see the video? I hope you can. So, so this is an animation of a star, a massive star, which is undergoing nuclear burning. As you can see, it goes through these different phases. And once nuclear burning halts, you will see that the star explodes. So these are the outer layers that explode, where the core collapses, and then the remnant formed is a neutron star. Now, this I already mentioned. So when the progenitor star is below 20 solar mass, the remnant formed is a neutron star. And this hot, newly born proton-neutron star cools slowly by emitting neutrinos. So neutrinos take away energy from the system, thermal energy, and the neutron star cools to become a cold neutron star that we observe later. But for heavier stars, so progenitor stars heavier than 20 solar masses collapse to form black holes. Now, a slide about the internal structure, although we are going to talk about internal structure more in the next talk. But so like we said in the white dwarf, the nuclear burning stops at the level of carbon burning in the core. So the structure is like this. So there are hydrogen shells and helium shells in the outer layers, while the core is formed mainly of carbon and oxygen. On the other hand, neutron stars have much more complicated structure. So this again, I'll come in the next talk. So there's an atmosphere, an outer crust, inner crust, an outer core, and an inner core. And these are, so there is a vast range of densities which is covered, and therefore the composition of the internal composition of neutron stars is extremely complex. So we'll discuss this in the next lecture. Now, let's see what we can find out about neutron stars from their observations. So I'm primarily now concentrating on neutron stars because, like I said, they are one of the densest forms of matter in the universe, and also they are observable throughout the electromagnetic spectrum. So the visible range, so the stars that we see with the naked eye in the night sky, they are only within this small part of this entire electromagnetic frequency band. So now we have at our disposal a large number of telescopes. So some of these lists, the names that you see here are already functional, and some of these are proposed missions. So these are together scanning the sky throughout these different frequencies, from gamma rays to X-rays, ultraviolet, infrared, microwave, up to radio frequencies. So these are ground-based and space-based telescopes. And together, so multi-wavelength astronomy is making it possible to understand the rich physics of different objects like neutron stars. So to give you an example, this is the Crab Nebula, and seen at different frequencies. So these are different, so all these these ground-based and space-based telescopes that you saw, these are observing systems like the Crab Nebula. And as you can see that in the visible, near infrared and radio frequencies, you see this interstellar dust in the nebula, whereas in the X-rays you can see this the Crab pulsar at the center of the star, which is the neutron star. So to understand neutron stars, let's look at a little bit of the history and how it was found that pulsars are neutron stars. So we said already that Chandrasekhar showed in 1931 that massive stars collapse. Then Chadwick discovered the neutron in 1932. Although neutrons were predicted earlier by Majorana, but these were never published. Barde and Zwicky introduced the concept of neutron stars. So in 1933, they proposed that these neutrons that Chadwick discovered can actually constitute a compact object called a neutron star. Then 1939, Oppenheimer and Volkoff computed the stellar structure and masses of these neutron stars using general relativity theory. Then Jocelyn Bell, you know that as she was a young PhD student at the University of Cambridge, she was looking for quasars with the help of radio telescopes that she herself constructed. And finally, she found some scribbles in the frequencies that she detected. So she went back to later again to these observations and tried to understand what is this very, very periodic source of radiation coming from this particular region of the sky. So Gold and Pacini proposed the basic lighthouse model for the neutron star in 1968. So this model said that actually neutron stars, when they rotate, because of their strong magnetic fields, they can emit radiation, a beam of radiation, because of the stripped charged particles, and this beam can sweep the Earth like a lighthouse and produce these very periodic pulses every time they are received on Earth. So now this was understood that the pulsars that Jocelyn Bell discovered in 1967 are actually rapidly rotating neutron stars. So this was the first discovery of neutron stars in radio frequencies. So now we have, as I said, a large number of telescopes which give us a lot of complementary information about the different properties, different observable properties of neutron stars. So spin period, their mass, radius, temperature, magnetic field, and so on. And I will come to more of these in the next part of the talk. So neutron stars can be isolated, but they can also be in binary with other stars. So when neutron stars are isolated, so like I said, they are powered by the magnetic field, so the rotation, so they are also called rotation powered because it's through this rotating dipole mechanism that this magnetic field is generated. And as the magnetic field decays, the pulsar loses its pulsing mechanism with time. On the other hand, if neutron stars are in binary with another object, so like say another neutron star or a white dwarf or even a normal star, then they can accrete matter, which means that they can suck up material from this companion star, which spins up. So it actually accelerates the rotation of the star. And so these are also called accretion powered pulsars. So this is a complex evolution of pulsars, and there are different studies of evolutionary mechanisms in pulsars, which suggest that accretion powered pulsars can actually go through several like interactions with the companion star, like through Rho overflow and this. So you can read more about it in the reference books that I will refer to in the end of my talk. And so what it can also result in double neutron stars. So like at the bottom you can see this picture of a double neutron star. Somebody raised their hand, is it? I will have to stop share. Should be able to see. Yeah, okay. I see 3 hands up. So maybe, I don't know who was first. Can you please unmute yourself? Or maybe I can just go one by one. Can I unmute you? I'm not being able to unmute. Jishna, can you unmute?
Hello, ma'am. Am I audible?
Yes, you are audible.
Thank you, ma'am. Ma'am, my question was the pulsars that you just said, they are mainly powered by the magnetic field of the neutron stars, and they are the radiations that are just emitted at very high speed. So my question was, the pulsars, are they consist of only radiations, or they consist of some matter also? And is it coming from directly the neutron star or from the magnetic field layers?
So I will come to the discussion of the magnetic field in the next slide, but let me again show you the picture of the internal structure. So you see on the right hand side the internal structure. Maybe I should have said a little bit more. I can say this now. So neutron star is composed of matter, yes, and as we go from the surface to the interior, let me tell you what we find. So there is an atmosphere which comprises of hydrogen mainly, and then helium, carbonate. There's also a debate about what is the exact composition of the atmosphere. Then as we go towards the interior, the density increases. So you find in the outer layers of the crust iron light nuclei. But then as the density increases, the nuclei that you find become more and more neutron rich. And these nuclei are embedded in a sea of electrons. Then beyond a certain density, which is also called neutron drip density, you find neutrons start to drip out of these nuclei. So this part called the inner crust is made up of nuclei, electrons and neutrons, neutron rich nuclei, okay? And then these nuclei, as the density increases, you find these nuclei are not spherical, but they become distorted into different shapes. And finally, at a certain density, they dissolve to form a homogeneous fluid called the outer core. And this comprises of neutrons, protons, and electrons mainly. It's mainly comprised of neutrons, though, which is why it's called a neutron star. But there is a small fraction of electrons and protons. But the inner core, again, inner core is a region where the densities cross that of the nuclear densities that we see in nuclear experiments, and they can go up to even 10 times. And the physics of this part is extremely complicated, so I'm going to talk about this in the next lecture. But like I said, so this is matter, okay? This is matter, but so matter in the sense, again, outer crust is a small layer. The outer core is mainly what is comprised of neutrons, and these form 99% of the entire mass of the star, which is why we call them neutron stars. And so these charged particles, like I said, these electron, protons, so these are stripped from the star, and these are what are stripped by the magnetic field and produce these beams of radiation. But then radiation that you see from the neutron star come from many different levels. So when you observe neutron stars at different frequencies, there are many different sources of radiation. So sometimes it is the neutrinos which are coming out. So the thermal neutrinos, which are seen in X-rays. Sometimes it is the accretion, when you're accreting matter, when the neutron star is accreting matter from the companion, then these form hotspots, and these hotspots are also glowing. So again, this radiation mechanism is coming from the interaction of neutron stars at many different levels. I hope this answers your question. I mean, this is difficult to answer in just maybe one or 2 lines.
It was quite complicated. Thank you.
Who's next? Can you please unmute yourself? Saurav, maybe? Yeah. Please go ahead. Saurav, can you go ahead? Am I there?
Good morning, ma'am.
Hello, Abhijit. Yeah.
Ma'am, basically, I have a question regarding that accreting, the matter accreting around the neutron stars. Ma'am, is basically due to it is gathering mass from the other stellar body. So, is it possible in the future that it become a black hole or something?
Yes, so like I said, so this evolutionary mechanism is quite complicated. So you can refer to some online lectures as well as some, because this is like this would be an entire lecture by itself. So I don't have a slide for that, but there are many different, like depending on what it is interacting with. If there are two neutron stars, if there's a neutron star white dwarf, if there's a neutron star normal matter, then when it accretes matter onto the surface of the neutron star, it can happen that this second neutron star spins up, and then at a certain point this also goes supernova. So this supernova can again result in formation of another neutron star. It can also go into a black hole. So this is quite a complicated interaction mechanism depending on the masses of the stars and what kind of companion it has. Who is next? Yeah, sure.
Hello, madam.
Yes, hello.
Madam, you showed you tell us that neutron star rotate due to its magnetic field and it's radiate, and we get a pulse. And in the next video, you showed us the rotation power pulsar mechanism. And can you further elaborate that how this animation is related to that peak?
I mean, this is not a scientific illustration, but I will come to the discussion of the magnetic field in the next slide. So I think some of your question might be answered there. I'll come to it. Yeah. Who's next? Shari or Jishna, do you want to unmute yourself? Anyone else?
Good morning, ma'am.
Hello, good morning.
Ma'am, I got to know that these pulsar emissions that are produced, they produce at some particular height above the magnetic pole. Am I audible?
Oh, can you repeat the question?
The pulsar emissions, they produce at a particular height above the magnetic pole. So I just wanted to ask, why is that? So is that also because of the magnetic field?
Oh, so I am not going into the detail of the pulsar mechanism because again, this is all very complicated. I don't have any slide on the pulsar mechanism itself. Yeah, I mean, maybe you can refer to some textbook for now. I don't have a slide on that in this talk.
Thank you, ma'am.
Yeah. So I think I will continue because time is out. We can come back to the talks later as well. Okay, so let me go back to the slide on the magnetic field. Okay, so like we were talking about the magnetic field. So again, this is a very complicated physics of, I mean, this pulsar mechanism itself is quite complicated, and there are like different observations related to it, like pulsar wind nebula, etc. I'm not going to talk about the details of that, but what I will talk about here is, so in this talk, mainly I will concentrate on some of these observables and how they are detected. So like I said, so neutron stars spin and magnetic field, like we said, so for the rotation powered pulsars, these are related. And so in a very simple way to understand this, you can imagine a rotating magnetic dipole, which is at an angle to the rotation axis. And so this we know from like the Larmor formula for an electric rotating dipole. You probably are familiar with it. Probably also had some lectures in this summer school on radiation mechanisms, right? So this, if you equate the luminosity because of magnetic dipole radiation and that of the rotational kinetic energy. So what you will, if you equate these two, then you can come to a simple formula of the dipole magnetic field, which is related to the P and P dot, which means the pulsar period and the period derivative. And the rest of the terms here are like constants. Alpha is the angle, R is the radius of the star. So now, as I said, neutron star spins can be very accurately measured by pulsar timing. So you see these very accurate pulses arriving from a neutron star. So these, if you plot these, the log of the spin period on the x-axis and the spin period derivative on the y-axis, you see that there are these different populations of neutron stars plotted here. All interestingly, like from the P and P dot, using this formula, you can find out what the magnetic field in these objects is. You can also find the characteristic age, which means that if you integrate P and P dot, like this relation above, then what you find is something called the characteristic age of the pulsar. Another thing you can also derive from these is called the breaking index. So nu is nothing but the frequency. So you know that nu and p are related. And this breaking index is this index n of the, if you express nu and nu dot using this relation. So I'm again not going into the details of the calculation, but just to give you an idea, on the right hand side, you see this P and P dot plot. So the pulsars, the normal pulsars we were talking about, so these are clustered around the center, this swarm of particles, this swarm of points you see at the center. And you see that if you calculate magnetic field using the dipole formula, these correspond to around 10 to the 12 Gauss. So this is the normal pulsar. Then there you see there are other parallel lines corresponding to 10 to the 10 Gauss, 10 to the 14 Gauss, etc. So these are surface magnetic fields, which are observed from, which can also actually be observed directly with the help of cyclotron lines and so on. Again, on the other lines you see here are the characteristic ages. So 10 to the 12 years, 10 to the 9, 10 to the 6, and so on. So these accreting neutron stars that we were talking about lie towards the bottom left of this figure, because these are like I said, so these accrete material, they spin up, their magnetic field goes down. There is again a complicated evolutionary mechanism. So these, there is a theory of evolution of pulsars, like how their magnetic field decays and how they interact with their companion, etc. Another interesting thing that we can see here is this population on the top right hand corner. So as you can see, these all lie above 10 to the power 14 Gauss, which means they are extremely magnetic. So these are called magnetars. So there are different classes of these objects. Some are seen in gamma rays called soft gamma ray repeaters. Some are seen in X-rays called anomalous X-ray pulsars. So you see the importance of multi-wavelength astronomy. And these indicate some common features which show that they have magnetic fields as large as 10 to the power 14 to 10 to the power 15 Gauss. Later also, there are some other intermediate magnetic field neutron stars which have also been found, called X-ray dim isolated neutron stars, rotating radio transients, etc., etc. So these are intermediate between these ultra strong magnetic field neutron stars called magnetars and normal neutron stars which have 10 to the power 12 Gauss magnetic field. So why are these magnetars interesting? Because as you can see, we want to probe extreme physics, and these have extreme magnetic fields. 10 to the power 14, 10 to the power 15 Gauss at the surface. So interior can have even larger magnetic fields. And these objects can show a lot of different features like magnetar bursts and flares, and also they can be strongly deformed from the magnetic field can deform the neutron star from spherical to elongated shape. So this can also result in a lot of interesting physics. So maybe I can skip this slide. So this is just to say what are the different ways of detecting magnetic field. There are also other interesting physics you can determine from observing spin periods of neutron stars. So one of them is a glitch in the neutron star spin period. What do I mean by that? So usually when neutron stars are slowing down through this magnetic braking mechanism, they have a fairly regular omega versus t plot curve, like frequency reducing with time smoothly. But then different neutron stars, like say Crab and Vela, which are very well-known pulsars, so they show sudden spin change, sudden jumps in the spin frequency. Like you can see in this cartoon at the bottom, these so the dashed line is what would happen if it was smoothly slowing down, but then suddenly there are these glitches, and this is actually a repetitive behavior. So there is a glitch and there is a post glitch relaxation time, and then again there is a glitch. So now scientists were baffled as to what causes this kind of sudden jumps. There are different theories. First, scientists thought that this could come from crust cracking. But then most common theory now is that neutron stars, so these neutrons, protons which form the neutron star can be superfluids, and I will come to that also. So superfluidity means that superfluids on Earth, where do we observe them? In laboratories, in extremely low temperatures. So neutron stars, like I said, when neutrinos take away thermal energy, the neutron star is extremely cold. It's almost like zero temperature, and they have, so the particles forming the neutron star, these can become superfluid. And it is thought that we know from terrestrial experiments that when you put like a superfluid into rotation, there are vortices which are created, and these vortices can also be found inside a neutron star. So how amazing is that? So these vortices can again pin. So these are like some flux tubes, so some tubes of superfluid material which are at the top and bottom, they can get attached to the crust nuclei. And when there is a sudden, like there is a transfer of angular momentum between these superfluid and normal components, there is a sudden glitch. So as you can understand, this is a very complicated physics. There are different models and theories and so on. But the basic point is that, again, this is something that tells us about superfluidity in its interior, and this can be observed from the pulsar timing, the pulsar spins. Now, let me come to one of the other very important neutron star observables, which can be accurately determined, and this is the neutron star mass. And also, this is a very important observable in understanding what is the composition of the interior. So I will talk more about this in the next lecture. So neutron star masses are measured. So the most accurate masses that can be measured are for binary pulsars, or two neutron stars in binary. And what happens is that when two neutron stars are going around each other, from the analysis of their orbital motion, so if the pulsar is orbiting, like I said, a neutron star, white dwarf, or a main sequence star, then there are these orbital sizes and periods undergo Doppler shift. So there is a relative change in the frequencies because of Doppler effect. And from this, so from measuring these parameters, which are also called Keplerian parameters, because they are related to the orbit of the neutron stars. So this from the Keplerian parameters, there are 5 of them: orbital period, the semi-major axis, the eccentricity of the orbit, also longitude of periastron and periastron passage. So these are things that you can find in any normal astrophysics textbook. So these are Keplerian parameters. And from these parameters, once you measure these parameters, from this, the total mass of the binary can be deduced. But then in order to find individual masses of binaries, there is something else which is probed, and that is relativistic effects. So neutron stars are extremely compact, right? And therefore they have strong general relativistic effects. Their surface gravity is very strong. So what happens is, like, when there are two extremely relativistic objects like neutron star, white dwarf, neutron star, black hole, what happens is that these relativistic effects start to show up in the observed in the observables. So, for example, here there are 5 post-Keplerian parameters that can be determined. Post-Keplerian means that in addition to the Keplerian parameters, these are like next orders, corrections. So from these post-Keplerian parameters, it was like, this is something which is quite well known. So these post-Keplerian parameters, like advance of periastron, this is something like the Mercury also shows perihelion advance in the solar system. You might know about this. So this is advance of the star, periastron. The gravitational redshift and time dilation. So these are all concepts from general relativity. The orbital decay. So when the neutron star, and there are 2 neutron stars and they are actually emitting gravitational waves coming closer and closer together, there is an orbital decay. And Shapiro time delay. So which means that when there is a pulse arriving from a star and there is a neutron star nearby, it can cause a time delay because of general relativistic effects. So all these post-Keplerian parameters can be measured very accurately. And from these are all shown to be, I mean, I'm not going into the equations, but these are all related with the masses of the 2 neutron stars or the 2 objects in the binary. So for example, at the bottom, you see a picture of the double pulsar. So there was a neutron star system. So both of these neutron stars were pulsars. We could observe pulses from both of them. And this led to observation of a lot of like Keplerian, post-Keplerian parameters, which led to determination of the masses A and B, the companion star, the component stars in the binary, very accurately. So this is how masses are determined for double neutron star binaries. So you see here on the left hand side, this is a list of a compilation of the different neutron stars that were observed. At the bottom, you see the range of masses as well as their, so the dots are the masses and the lines next to it are the error bars, so the uncertainties in the measurement. So the uncertainties are the least for double neutron star binaries, as I just said. And on the top and bottom, you see there are neutron stars with other companions, like I said. So neutron star accreting matter from a stellar companion can be seen in X-ray binaries, but you see they have large relative errors. And this is because there is a difficulty in determination of parameters of the orbital motion, because there are accretion flows, there are things which are disturbing the observation. At the bottom, you see these are neutron stars in binaries with white dwarf companions, and these have a wider range of masses than the binary neutron stars. Recently, there are some observations which indicate that masses as large as 2 solar masses can be observed. So what is the importance of this? I will come to this in the next lecture. This is something which is actually telling us a lot about the internal composition of neutron stars. There are also some other observables that can be measured. So, for example, gravitational redshift. This is also something which is a concept from general relativity. So, redshift is basically the change in the wavelength. Lambda O is the observed wavelength, lambda E is the emitted wavelength. So there is this difference, the relative difference is called redshift. And it can be shown that this redshift is related to the compactness, which is the relation between mass and radius. So these, from X-ray observations, one can determine spectral lines. Spectral lines which are emitted from the atmosphere, or these spectral lines can give us an information about the redshift and therefore also the compactness of the star. Now, other things that can also be seen from X-ray observation. So one is the temperature. So temperature means the thermal evolution of the star. So from the observed flux and luminosity, so you see these F infinity and L infinity, these are observed flux and luminosity at the surface of the neutron star, and assuming that the neutron star is like a simple black body, one can determine its effective temperature. So this is called T effective infinity here. And from these, once the redshift is known, we can deduce the actual effective temperature. And you see this temperature is plotted here as a function of time, and these are different observations of pulsars which are plotted. And this is how the stars are cooling down. And actually, interestingly, recently there was an observation of a star which has a strange kind of cooling down, and so this was a neutron star in the Cassiopeia A constellation, and this is said to be because of a sudden change from normal to superfluidity again. So this is thought to be an observational discovery of superfluidity. So again, like you see these different lines, these are models which try to explain how these neutron stars are cooling down. And also the cooling depends on a lot of different things, the thermal conductivity of the star, which in turn depends on the composition of the star. So these will also give us information about what is there in the interior of neutron stars. Another very important observable is the neutron star radius. So there are also many different ways in which a radius can be determined. Unfortunately, none of them are accurate enough. So not like the mass or spin, radius measurements have large uncertainties. So for example, the most reliable neutron star radii and most trusted ones are from observations of thermal emissions from the neutron star surfaces. But then these radius estimates are affected by distance uncertainties. So if you see at the bottom, again, I wrote down the same equations. So relating flux, luminosity, and the radius. So this radius is also called the, maybe I'm missing something here. Yes. So this is called, the R infinity is called the radiation radius. So this is at the surface of the star, and this can also be determined from the flux, luminosity, and temperature of the neutron star given the distance. But then this is the main problem of radius determination. Pulsar distances can be obtained from dispersion measures, which means that you imagine that there is a column of interstellar medium, and you try to understand the composition of this. But then there are large ambiguities because of absorption of X-rays in the interstellar medium. You don't know the atmospheric composition or the magnitude of the magnetic field and so on. So pulsar distances are not well known. But then, again, sorry, I missed. So in the case of neutron stars in globular clusters, so in globular clusters, the distances are pretty well known. So in that case, measurement of radii can be comparatively more accurate. And the other thing is, if the atmosphere and distance, so these are the two main sources of uncertainty, if these are known for thermal emissions, then the radius can be determined. So this is, however, not accurate enough as in the case of masses. And so, yeah, on the right-hand cartoon, you see these accretion of neutron stars resulting in thermonuclear explosions, which are seen in X-rays, and so on. Recently, there has been a recently launched mission called NICER mission, so the Neutron Star Interior Composition Explorer mission. And so these have, what happens here is X-ray timing and spectroscopy of thermal emissions. So the hot and cold regions of neutron stars alter the shapes of these pulses. So in the bottom video, you see that there are these two hotspots which are obtained from mapping the neutron star surface and modeling the general relativistic effects of these pulse profiles from these hotspots can give us information about the redshift and therefore the compactness. So this is now a very hopeful case for giving us very accurate measurements of radii, maybe even up to 5%. Finally, moment of inertia is something that can be also determined from spin-orbit coupling or from glitches. And so this moment of inertia is also something which is proportional to mass times radius squared. And so once moment of inertia can be measured from any of these observations, and you have an additional observation of mass or radius, then the other can be determined. So I will come to this in the next slide, next lecture, as to how the internal composition can be related to the mass radius relation and how it gives us an idea about the internal composition. Finally, another observation that has opened up an entirely new window to the universe, and that is the observation of gravitational waves from binary neutron star mergers. So neutron stars actually can emit gravitational waves also from isolated neutron stars. So isolated neutron stars can, like I said, they can undergo different kinds of deformations, rotation, oscillation, and these can result in emission of gravitational waves. Any kind of non-axis symmetric perturbation can emit gravitational waves. So gravitational waves are nothing but this perturbation of space-time around neutron stars. So if there is a glitch or a flare that we already talked about, this can result in bursts of gravitational waves. On the other hand, if there are some deformations, like for example, we call it a mountain, so a bump on the neutron star surface, or strong magnetic fields like you see at the bottom, so deforming the neutron star, this can result in continuous gravitational waves. But another interesting thing is that just like we see on Earth for fluid oscillations or even for the sun, heliosismology, this is a field, well-known field, so there are oscillations inside the sun as well. Similarly, in neutron stars also there can be different kind of oscillations, and these oscillations can also generate gravitational waves. Interestingly, these different oscillations carry signature of internal composition of the neutron star. So once these are observed, they can tell you what the core composition is. Finally, binary neutron stars. So binary neutron stars were actually first indirectly determined by Hulse and Taylor back in 1974. So they observed this neutron star binary. So these neutron stars are emitting gravitational waves. They are coming closer and closer together. And this orbital decay is exactly predicted by general relativity. So they went and measured this and found it to be exactly following this prediction. So this is said to be the first indirect detection of gravitational waves, and it won them the Nobel Prize in 1991. Now, what happens is that so neutron stars in binary, what happens when they come closer and closer together, there is orbital decay. And this phase is called an in-spiral. So it's spiraling in. There is the merger that you see here in the cartoon, merging. And so merging results, it can result in different things. It can result in a wobbling, hypermassive neutron star, which finally can also collapse into a black hole. Or if this star is actually stable, then this can result in a ring down, which means it rings like a bell. There are different oscillations going on inside. And so why is this interesting? Because again, as during the in-spiral, the neutron stars, because of strong gravity, they tidally deform each other. So like the sun-earth tidal effects, and this is something which is also predicted from neutron star simulations. And so this tidal deformation is related to the compactness. So C, or inversely to the radius and mass, and therefore you see that here, this on the right hand side, there is a figure from recent observations of gravitational waves, and from the plots there are different models that can also be distinguished. So I will come to this in the next lecture. So you see gravitational wave detectors. So this is something that started back in already from 2000, I mean even much before than that, but then LIGO detectors that were built in the US at Hanford and Livingston, and the Virgo detector came up in Italy-France border. These were not sensitive enough to detect gravitational waves, but then after an upgrade, the advanced LIGO in 2015 was first time able to detect binary black holes, and then in 2017 for the first time detected a merger of gravitational waves. And interestingly, this merger was also seen throughout the electromagnetic spectrum by all these other multi-wavelength telescopes, and that gave us simultaneous information about all different models of gravitation of neutron stars. So they were seen in gamma rays by Fermi and integral, in X-ray by Chandra, by VLA in radio, and so on. And these told us a lot about the interaction models of neutron stars in binary. Finally, this is my last slide. So, as you know, that gravitational wave observatories, in addition to the LIGO and Virgo, there is also GEO, and there are many others which are coming up at different parts of the world. Kagra has already started operation in Japan. LIGO India is coming up, so I am associated with the LIGO India project. LIGO India is coming up in India, and also there are other missions like NEMO in Australia. So these are proposed missions. Einstein telescope, the Cosmic Explorer, and so on. So there are many different telescopes which are proposed for gravitational waves, LISA, and so on. And you can see at the bottom, so these initial LIGO sensitivity was not strong enough to detect gravitational waves from neutron star mergers. Advanced LIGO was able to detect it. Then the Einstein telescope gives us a lot of hope about being able to detect gravitational waves from these sources. And on the right hand side, you can see many of the sources that were detected in the last observing run. So here are some books for further reading. These are basic books about neutron stars that you can refer to, which have a lot more detail about the preliminary things I talked about in this talk. So I think now we can go to the questions. Let me, okay. Yeah, please unmute yourself. I don't know who was first. Tanmoy, maybe you can unmute yourself. Yeah, please.
Am I audible?
Yes.
Ma'am, I have two questions. First is, what parameters make the magnetar such a high magnetic field? Is there any effect of neutron degenerate space of exterior, interior is high or low, something like that?
You are asking what is the source of such a strong magnetic field?
Yeah, ma'am.
So this is actually not known. I mean, there are different models which are trying to explain the strong magnetic field. It is thought that there are different explanations. So first of all, if you look at the progenitor star, it has some magnetic field. So when it is collapsing, because of conservation of magnetic flux, as the radius decreases, the magnetic field blows up. So this is explanation as to why normal neutron stars are strongly magnetized. But then why can you have certain neutron stars which are so highly, like even 10 to the 15 Gauss? So this is not well understood. It is thought that there might be something called an alpha omega dynamo effect. So this dynamo actually increases the field. There are also suggestions of a magnetorotational instability which can pump up the magnetic field. There are simulations which are trying to explain it, but then what is the source of this field is still not well understood. But then in general, magnetic fields are produced by currents of charged particles, and therefore since we have electrons, protons as charged particles mainly inside the neutron star, there can also be some charged baryons. I will talk about this in the next lecture. These are in very small fractions, though. And so this is the source of the magnetic field itself. But then why you have such large fields of magnetars, this is still an active area of research.
Okay. Ma'am, my second question is, from a galaxy, if a light is coming and we are detecting, and it can be distorted by gravitational redshift with the kinematic redshift of the galaxy. So how can we accurately measure the dynamics of the galaxy, as how we can filter the gravitational redshift effect?
In this talk, I have not gone into the details of how exactly this is done, But then, I mean, there is a lot of modeling that goes into it. Not only that, on all of this, like mass, radius determination, gravitational redshift measurement. So you will have to refer to some detailed textbooks about this or some recent lectures, because I mean, there is a lot of modeling that goes into this. I mean, this is not a straightforward calculation, I would say.
Okay, ma'am. Thank you very much.
Sure. Who's next? Junik, can you unmute yourself?
Hello, ma'am. Thank you for the lecture. It was really beautiful. Ma'am, my question was, when we are observing a pulsar from a rotating neutron star, that thing counts as a periodic curve. And at the same time, when we are observing the glitches, that also counts as a periodic term. I mean, the glitches are continuous, right? They occur only once, or they continue as a periodic sense?
Yeah, I will show you the glitch picture again.
So my question is, how can we classify between these two? Like, which one is the pulsar curve, or which one is the glitch one?
Yeah, on the right hand side, you see this picture, right bottom figure. So you see, oh, sorry. So you see here, this is from the Vela pulsar. So you see this dashed, sorry, this red line. This is the relative change in omega, the periods of rotation. And you see that this is a smooth, this has a smooth slope, right? And then on top of that, there are these, there is a changing, what should I say? This tear-like glitch that you detect on top of this. So you see that they have different time scales. So you can actually detect them from pulsar timing very accurately. So one is a smooth spin down because of the field, and the other is this glitch effect superimposed on top of this. And these two can be entangled quite clearly.
Okay. So these things are like the glitches are of higher value or higher as compared to those.
I mean, much more frequent, right? Much more frequent.
Okay. Okay.
Not much more frequent. Sorry, this is in the case of Vela. But what I can say is that, so the neutron star normal pulse period, this is related to its rotation frequent. What am I saying? Yeah. So the pulses that you are receiving, it's like every time the pulse, the star goes around, right? On the other hand, glitches happen much less frequently. So much less frequently in the sense this transfer of angular momentum does not happen every time there is a rotation. And also this has a different nature. Like I said, there is a sudden jump in the spin frequency, and there is a slow post relaxation period. So these two can be entangled from the timing studies.
Okay.
They are different times. Different times.
Yeah. Okay. Thank you.
Yeah. Next, who's next? Shia.
Good morning, ma'am. Ma'am, my question, am I audible?
Yes.
Ma'am, my question is from the determination of the mass of neutron star. So you talked that the neutron star mass can be determined through the binary system, the relativistic binary masses. So why is it so that it is better, or it is determined only from the binary system and not from a single neutron star?
So, I mean, how can you measure a single neutron star? That is the question. I mean, in the case, I mean, I don't think there is a mechanism to measure something. I mean, a neutron star mass, an isolated one. So mainly, we detect masses through interactions of neutron stars with something else. So either it is like when it's going around something. I mean, in general, if it was not a relativistic thing, so Keplerian parameters. So this is something which is used even for the case of, say, the solar system. So Keplerian orbits. So this is something we know from general astronomy, the Keplerian behavior of the orbits. And when you have this kind of orbital behavior and you are observing the pulses coming from them, so what are the changes in the pulse periods because of this orbital motion? This is how you observe it. In the case of X-ray binaries, there are also other interesting effects. So for example, there is eclipse. So you know that in the case of Sun-Earth system also, you have eclipses. So one goes behind the other. So in that case, you will see a sudden drop in the pulse period because of this eclipsing. So from that also you can say something about the masses. So mainly masses are determined with, so like you saw in this plot, masses are determined by interactions of neutron stars with something else. And like I said, the others have more uncertainties. In the case of two neutron stars, this is more accurate. But there is no way of determining just one single neutron star mass. I mean, we cannot go there and wait, right? So we don't know how to measure something unless it interacts with another companion.
Okay, ma'am, I have one more question. That when you talked about gravitational redshift, so ma'am, it is the change or in wavelength we observe due to the gravitational effect. So, ma'am, we are observing here from Earth that there is a change in wavelength, that the observed wavelength we are observing. So how do we know that this emitted wavelength is different? At first, how do we observe the gravitational redshift? How do we came to know that there is something called gravitational redshift happening? We can't go there and measure that what was emitted wavelength.
No, I mean there is there is an emission from the surface seen in X-rays, right? So for example, in this cartoon at the bottom, you see there is a hot spot, say, and this is seen in X-rays. So the neutron star is emitting radiation at a particular frequency. Let's call it omega emission. What am I saying? The lambda emissions. Okay. So now, when you are observing this wavelength, because of relativistic effects of, as general relativity says, so when we observe this, there is a change in the observed lambda because of the space-time, because of the effect of the space-time. And how it changes, you can calculate it given a metric, given the metric of the neutron star. You can actually see how much the strong gravity of the neutron star, how it changes the frequency that we observe. So this is, this is basically because the radiation emitted is passing the strong gravity of the neutron star, and it is having an effect on it. So when we are observing it at a shifted frequency, and what is this shift is determined by the metric, and the metric depends on the mass and radius. So this is how we know that how we can measure the compactness. And like I said, so this spectral line, so when like from the radiation, you can there are, say for example, you can measure these oxygen lines, iron lines. So this is for one accreting system. On the right hand side, you see this figure. So from these spectral lines, you can determine the redshift, and from the redshift you can determine the compactness.
Oh, okay, ma'am. Thank you.
Okay, who's next? Please go ahead. Yuvraj?
Am I audible, ma'am?
Yes.
Okay, so my question is on the analogy of superfluids in a neutron star to explain the neutron star glitch. The fact that we can see neutron star in the EM spectrum gives, we can safely presume that at least the outer surface of the neutron star should have some temperature. And if the core or a region near to the core, if it is of superfluid, we can come to a conclusion that it is nearly in the 0 Kelvin temperature. So in order for the vortex or the superfluid to stay there for a limited period of time, will there be a mechanism where a temporary shielding region happens between the outer surface and the inner surface where the temperature does not reach the core due to the heat?
Okay, so let me again share this just for reference. So, neutron stars, I mean, they are, for most of its interior, it's cold. It's cold. I will come to this in the next lecture as well, but the thermal emission we see is really from the surface. I mean, I think I will come to the details of this because I will talk about internal composition in the next lecture. So you will be able to.
Okay, thank you. Yeah.
Rafi? Oh, I think I'll have to stop. This is the last question. Yeah.
Good morning, ma'am. Am I audible?
Yes, please.
Yes. I might be wrong. You mentioned that the outer part of the neutron star is composed of homogeneous fluid, I guess, composing of neutron, electron, and everything, which is distorted. So my question is, in the gravitational redshift slide, there is a spectral line of emission, spectral line of iron. So how can we tell that that's iron? And that was the question. That when that's the homogeneous fluid, then why we are saying that it's iron? Or
these are from the atmosphere. These are from the atmosphere.
Okay. Thank you so much. And there's another question, please. What is the cause of the shock wave of the
the shock wave is because of these outer layers are falling towards the core of during a supernova, and then there is a rebound, and there is a change in the relative velocity. So this results in a shock wave. Okay. I think I'll have to stop here because the next speaker will start soon. So thank you very much. I think there are the questions from chat, and most likely I will be able to answer them in the next talk. Okay. Thank you very much.